So we saw one way of combining two hyperbolic polynomials in the same direction by just multiplying them, and so that allows us to construct other hyperbolic cones. Let me show you another construction that you have seen many times in the previous lectures, and that's the fact that if I take a hyperbolic polynomial in direction E, so that's P of, so if I look at P of x plus T E or x minus T, whatever, and so if this has real roots, we know that if this has real roots, we also know that its derivative by Rolle's theorem has also real roots. So we can actually construct other hyperbolic polynomials from P. And so, for example, we could look at the first derivative would be to take the derivative of this with respect to T and evaluate that in T is equal to 0. And so, so this is Q of x. So let's call this del P in x. And so this is also going to be hyperbolic in direction E if P is hyperbolic in direction E. And so we can repeat that. And so we could get a sequence P, del P, and so on. So we could get a sequence of polynomials which are hyperbolic in direction E. And because of interlacing of the zeros, we can actually even see that if I look at, so interlacing implies that if I take the cone corresponding to P, that will be contained in the cone corresponding to del P, and so on. So we have a sequence of such cones. So let's first look at whether we can get a nice description of these cones. So remember the result of Renegade that I had mentioned, and that was if I express P of x plus TE, and I write it as PE times T to the D plus, I think it was A1x, T to the D minus 1 plus A D minus 1 of x, T plus AD of x. Now, if this is the expression from P of x plus TE, then I can easily get the description of del P of x. And so that's I take the derivative of this with respect to T, and then I get rid of the, so I get del P of x plus TE is going to be whatever. So you can differentiate. And I'm sure you can differentiate. So in particular, what it means is that, remember that I had said that the hyperbolic cone corresponding to P could be expressed as the set of x in Rn. such that all these polynomials, a1 of x is positive, and so on, up to a d of x is positive. And so that means that we get a representation as a semi-algebraic set of the derivative. So these are called derivative relaxations. So we get one cone and then a bigger cone and so on. And the k plus corresponding to the derivative of p is going to be so when I differentiate, I get all these terms, all these a sub i's times a factorial of some term, but I will get that this is simply the so a1x up to ad minus 1 of x is positive. And that in particular shows obviously that it must be a subset of. And more generally, kp of delta I of p is going to be the set of x in Rn, such that you go up to a1 and you go up to a d minus I of x is positive. So for example, if you take let's say the very basic hyperbolic polynomial, which is just the product of the x sub i's, the first one is actually the positive orthant, and that can be expressed as all the elementary symmetric functions being positive. And then as you take these derivative relaxations, you get bigger and bigger cones, and you only look at some of the elementary symmetric functions being constrained to be positive. Now, so one thing that Rennegan also observed is that Rennegan also observed, so from an optimization point of view, that's interesting is that if can evaluate p efficiently, we can actually then can evaluate also any of these relaxations efficiently. So can evaluate the ith derivative of p efficiently as well. And this is easy to do. It simply comes from the fact that you'd like to evaluate when for example, del p of x is going to correspond to ad minus 1 of x. So you'd like to evaluate the coefficients. You'd like to find the coefficients of these polynomial, and because all these, when you evaluate in t is equal to 0, will correspond to one of these terms times the appropriate constant. And but to compute these terms, you can just evaluate these polynomial for several values of t, and then just do interpolation. So you can use discrete fast discrete Fourier transform to get these.
I think you don't want to evaluate at t equals 0, the definition of the derivative. Because everything will go away, only ad minus 1 will stay.
Right, but when it's true that so it's true that del p of x is indeed a it's going to be AD minus 1 of x times PE. So it's going to be, so if you like, P of x is just P of E times AD of x. Del P of x is going to be P of E times A D minus 1 of x. But when you apply this operation one more time, you have to add TE, and you will get all of these. So because you can evaluate these, again, using interior point algorithms, using these theory of self-concordant functions that was established by Nesterov and Nemirovsky, you can actually not just optimize efficiently over hyperbolic cones that correspond to a P that you can evaluate, but also these derivative relaxations as well. So, so for example, if you take let's say semi-definite programming, so if you take the cone of positive semi-definite matrices, so that says that all the elementary symmetric functions of the eigenvalues should be, let's say, non-negative, or positive if you take the positive definite code. But then you can actually, if you look at only the first D minus I, you can still optimize over the set of symmetric matrices such that these D minus 1, D minus I elementary symmetric function of the eigenvalues are positive. So that's something that was, I mean, when people were looking at semi-definite programming, that was not completely obvious how one could do that. So
in your definition of the derivative there, do you need to set t equals to 0? Because if you just take the derivative, then you set to 0, you're only left with AD minus 1. How do you recover the A1 x greater than 0 in your...
I guess now that there are two questions, maybe I should look at it more carefully. If you... Okay, so 1 second. You take...
I think when you evaluate x plus TE, you get A minus. But when you evaluate x, you just get A minus 1.
So I think you get the A1x when you then, sort of to get k del p, you need to look at the roots of the polynomial del p along x plus te. Oh, so you again get a polynomial in t, and essentially you get A1x again as a coefficient somewhere.
Right, so I think that...
Only getting AD minus 1 of x, right?
But then you have to plug in x plus te into this polynomial and expand in t,
so,
and then you get more.
Oh, and then you get more again.
Yeah.
Okay.
And you don't have to set t equals 0 directly.
Yeah, you could, yeah.
Two derivatives and then...
And then set t is equal to 0.
Same. Oh, okay. So, thanks.
Good, thank you. So,
Other applications of this?
So this is this is a very good question. So it's a, I mean, in my opinion, it's a beautiful framework. However, there is not. I mean, in terms of the optimization point of view, I don't think there is a great application of it. I mean, so for example, if you look at if you look at, let's say, semi-definite programming, one thing that I find interesting is that, for example, if you look at the stable set polytope of a perfect graph, so that's a polytope that has an exponential number of facets, you can optimize over it efficiently, you can separate over it efficiently, but the way you do that is by formulating it as a semi-definite program and then optimizing over that theta body of Lovász. So that's the results of Grötschel, Lovász, and Scriven. So even though you have a polyhedral set that's reasonably well understood, one doesn't know how to use the techniques of linear programming to optimize over it, and one needs to go to semi-definite programming. It seems that the same story could happen here someplace, and it's up to one of you to discover is to that there could be so for example, I mean, I'm really wondering about these matching polytope, because we can optimize over matchings efficiently in polynomial time. We can, if we look at the matching polytope, we can separate. So if I give you a point, I can find an inequality that's violated in polynomial time, or prove that that point is inside the polytope. And I can do all kinds of things, but there is no, I need to use, for example, the ellipsoid algorithm to be able to optimize over that polytope, or do it combinatorially. But would be neat if I could show that it can be viewed as the hyperbolic cone, I mean, as a section of an hyperbolic cone, and be able to, I mean, so for example, there are some, I haven't discussed that, but there are some hyperbolic polynomials that arise from Pfaffian. And so that might be a way that possibly one might be able to get to matchings, but I really don't know. So I think I think it's an interesting question. So even if for example, if let's say that that the generalized Lax conjecture, let's say, is true. So suppose it's true. So,
yeah, if you have to go very high.
Exactly. If you have to go very high, it doesn't. So in terms of optimization, it doesn't mean that much. So there might be some. I mean, even though it would show that it's not more powerful than semi-definite programming in terms of representation, but it could still mean that one could do it much more efficiently by looking at these hyperbolic things.
Is there like a randomized version of randomized surroundings, or just a hyperbolic setting? Because there is one for linear programming, right? There is one for semi-definite.
Not that I know of. So, any other question? I mean, I wish there would be. The answer was yes. So that's my hope, and so one of you should be able to do it.
So just one comment. So we have some papers which we don't use hyperbolic, cone, but we use hyperbolic polynomials, like elementary symmetric polynomials, for optimization. Because they are, like, we use the log concavity of these polynomials. So, like, for example, for Nash welfare, like, you will hear about it sometime in this program. But, so I'm saying, okay, so you can, this gives you log concave polynomial, you can do optimization over it, and then you can use it. That we have used. But, yeah, I agree, we haven't used the cone that defines what is polynomial.
Okay, so I mentioned initially that I was going to talk a bit about the connection between hyperbolicity and so hyperbolic polynomials and stable polynomials. So let me state one basic result, very simple. So remember the notion of stability. If I take a polynomial, let's say over the complex, we say that it's stable if I have if let's say x is in h to the n, where h is the set of x in C such that the imaginary part of x is positive, that if I have an x which is in the upper half plane, then that p of x is non-zero. So I guess you probably have seen mostly real stable polynomials, so these are with real coefficients, but that's the notion more generally. And so one can show the following. Many of the hyperbolic polynomials that we have been discussing are actually hyperbolic for the entire non-negative entente. And so if you have a polynomial p, so if you have a real polynomial and it's homogeneous, then it's going to be real unstable, if and only if P is hyperbolic for all non-negative, all E which are non-negative. So so that's a and this is very so that should be a 2-minute exercise. You can easily show that if P is stable, then if you take any non-negative direction, it's going to be hyperbolic, and vice versa. So that's one relationship between the notion of stability and hyperbolicity. I should emphasize that, I mean, a very simple trick is that when it's homogeneous, which half space you consider doesn't matter, because you can always, so for example, I could have defined this to be as the half space corresponding to the real part being positive, for example, because you can always multiply and not change the variety. So good. Let me maybe so let me go back to convexity because of the hyperbolic polynomial, because I think this was this is a very important result, and let me I claim that if you have a hyperbolic polynomial in direction E, and then you take a point in that hyperbolic cone, that the polynomial will also be hyperbolic in that direction. So let me prove that, and I'm going to, I mean, this was proved by Ganding a long time ago, but let me use the exposition of Peter Branden in one of his surveys. So let me show the following, that let me take a polynomial. Let P be a homogeneous polynomial. Be homogeneous. And two vectors which are not roots. And now let me first assume that P is hyperbolic. So that's a real, of course. I mean, it's a real polynomial. P is hyperbolic in direction E, and let's assume that an F belongs to the hyperbolic cone. And so I'd like to show that this is equivalent to saying that if I look at a bivariate polynomial in SNT, which maps to x plus, and this should be for every x. So if I look at the bivariate polynomial which maps to P of x plus SE plus TF, that this is a stable polynomial for every x. And so out of this, so one thing that's pretty obvious, since this is symmetric in ENF, is that so we'll show that the two are equivalent. That these two statements are equivalent. So once we show this as a basic corollary, it means that since this is symmetric in ENF, it shows that if P is hyperbolic in direction E, and I take a point which is in the hyperbolic cone, then it will mean that it's also hyperbolic in that other direction, and E belongs to the corresponding hyperbolic. So I should say K plus of E is corresponding to E. So that means as a corollary, we would have that K plus of E is equal to K plus of F, and P, so P is hyperbolic, and P is hyperbolic in every E, in every F. And K plus so let me prove that lemma, because that's really the, let me prove it maybe on another blackboard. So let me first show that say 2 implies 1. So I need to show that, so I'm assuming that this bivariate polynomial is stable for every x, and I need to show that it's hyperbolic in direction E. So I need to look at P of x. So I need to show that it's hyperbolic in direction E, and that f belongs to K plus. So so I'm going to look at this polynomial, and so the first thing I'm going to do is that I'm going to, so I know it's stable, but I'm going to take a t that's in the upper complex plane. So I'll take, let's say, t to be let's say epsilon I, where epsilon is positive, times t. And so if I look at, so epsilon I times f. So if I look at the roots here, since these are positive imaginary part, I know that the fact that it's stable means that a root will have non-positive imaginary part, and so this is going to be, so this is stable. This is stable in S, and since the bicontinuity of the roots, this is also true if epsilon tends to 0. So that means that this polynomial p of x plus se as a polynomial, as a univariate polynomial in S, is also stable for every x. So so that means that this is a univariate polynomial x, and so E and F, of course, are in on N. So E and X are in Rn, and so that means that since it's stable, it means that the roots must be cannot be in the upper half plane, but since it's a real polynomial, they will come in conjugate pairs, and so that means that the roots S are real. So that's precisely the notion of hyperbolic. So that's the first part. The second part is slightly longer. So if I take, so now I am assuming that I have a hyperbolic polynomial in direction E, and that f belongs. Did I show? No, I'm not done yet.
Don't you have to prove that the roots are?
Yes. Yes. I was just noticing that. Yes, I'm not done. I have to also prove that f belongs to. I have to prove that f belongs to it. Is hyperbolic in direction E, good. And so f belongs to it. So now I'm going to look at if I look at to write it down now on my notes, so I'll have to we discover it, or someone who wrote the original proof, Michael?
You set x to 0.
Yeah, so if I set x to 0, and I look at P of SE plus TF, now, so I need to look at
And then you can write it as a product of over the eigenvalues.
so so as a product over the eigenvalues.
Can you just set one of the variables to 1, and then if it's stable, then it's univariate, then it's real rooted?
Yeah, but you need the eigenvalues to be positive. But if you write this as a product over
So
set t equals to 1, you will get s plus lambda I.
so if I set this t to 1, I set t to 1, and so now I get that this is the product. What did you say? S is equal to?
So if you set t equals to 1, you get the product over s plus lambda I, where lambda I is the eigenvalue.
Of f, right? Lambda
Right.
Yeah.
S plus lambda I of f, yeah. So S of lambda I of f, yes.
And then you can introduce the t again.
And then, and so the, so what I need to show is, I lost what I need to show. So I need to show that that S.
So if you introduce the t again,
Right. Then it's done.
this has to be stable. So the lambda I cannot be negative.
So, isn't it the same as to argue that if we indeed take epsilon greater than 0, but positive, right, then the roots S cannot line the upper half plane, and therefore if you take epsilon go to 0, they cannot jump into the positive.
Yeah, but
Right.
But if you set, yeah, if you introduce the t on the right hand side now, so s plus t lambda I has to be stable, so lambda cannot be negative. Then, yeah, s minus t is not stable for long.
Okay, that was an exercise.
That was an exercise for me, not for you. Okay. I think I got that. I mean, you got that, but I think I understood. So, does everyone agree? No.
Because the linear forms.
Goemans proofs.
Yeah. X minus y.
So,
At the polynomial on S and P is stable, so they have to have the same sign.
right, yeah. Okay. So,
And you're using that lambda I of PF is T times lambda I of F as well.
yeah, lambda I, yes, right, exactly. So, yeah. Good. So that's the first one. For the second one, so if P is so if P is hyperbolic in direction E, and then I look at so I want to show that So let me first, so I want to show that this is stable. So I'm first going to fix an S, let's call it S0 in the upper half plane. And so now if I look at the roots of the polynomial that maps T to P of x plus S0 E plus TF, I need to show that this is stable. So let me first look at the case in which, so first let's look at x is equal to 0. So when x is equal to 0, I have the polynomial this polynomial, and so I know that so this polynomial is going to be so let me move either as 0 or t. Since I have, so let me move t. So this is t to the d times the polynomial S0 divided by t e plus f. Now, so this is a polynomial of f plus something times e. And so I know that since it's hyperbolic in direction E, so this better be real, and also it better be, so S0, so if I have a root, if I have a root, this better be S0t minus 1 should better be real, and also it better be negative. So and negative, and so since S0 is in the upper half plane, that means that t is such that its imaginary part, since the imaginary part of S0 is positive, then the imaginary part of t is going to be negative, and so that means that indeed this polynomial, in the case of x is equal to 0, is indeed stable. So that shows that that gives the case for x is equal to 0. So this polynomial is stable. Now, when x, so suppose that there is an x such that this is not true, then it's not stable. So what we'll simply do is we'll simply go from x is equal to 0 to so assume that there is an x such that from st to p of x plus se plus tf, that this is not stable. So let me take, so if I look at so that means that, but actually let me fix S0. So let me look at, so let me show that this polynomial is stable. So let me look at this. So see, if this is not stable, what it means is that I have a root here such that t is not in H. So if t is not in H, but t was in H when I was looking at roots of x is equal to 0, it means that between x and that x, this x hat and x hat, that along the way between x is equal to 0 and x hat, I have a root that goes from, by continuity of the roots again, by continuity of the roots, I have a root that goes from imaginary part less than 0 to imaginary part bigger than 0. And so there must be a value for which the polynomial, which is p of a multiple of x plus S0e plus, so I would have a root which has real, so in which t is real, and that's a root. But that's a contradiction because this is real, and that is real, and so I have, if I look at the definition of hyperbolicity in direction E, it means that from that point, if I look in the direction E, the root should be real, while S0 is not real. So that shows again that this is stable, and since that was for every S0, that means that the polynomial is stable. So that was a bit of a slow exercise for me, but it's getting late. So one other thing that I wanted to mention, but I think I already so was in terms of so we already kind of mentioned it before, but so when we looked at regular matrices and also and these spanning tree polynomials, we looked at the multilinear case with actually even coefficients which were we looked at, for example, sum over b in b of xb. So I'm looking at coefficients which are units, I in b of xi. And so we saw that, for example, if we take the if we take the basis of a regular matroid, that this is hyperbolic in actually any direction in the positive orthant. And so so one question that one could wonder is for which b is this p of x hyperbolic in direction. So since this is a polynomial with positive with non-negative coefficients, we could for example, for hyperbolic in direction E, let's say, of all one thing. all one vector. So, so one thing that was proved by Oxley. Sokal and Wagner in au fond is that actually that if P of x is hyperbolic, then actually and let's assume that actually we're in the homogeneous case. So let's assume that B is actually a subset of let's say n choose D. So if P is hyperbolic, then B must be the basis of a matroid. And so so there are various ways of showing this, but unfortunately the converse is not true. So this is not true, so matroid which come for which P of x is hyperbolic could be called hyperbolic matroids, and they often are called. I mean, at least in that paper, they call it with these upper half plane properties. So these are the upper half plane property, or the half plane property, or half stage property. So what?
So this theory is with respect to which direction?
So let's say all ones, or actually since. You can take. I mean, so if you look at the if you look at the cone, it's going to contain at least all the entire positive orthant. So you could use anything in the positive orthant. And so but the converse is not true. And so, for example, there are quite a few of these that are not. Quite a few matrices that are not hyperbolic. So. We know that the regular matrices, have that property. Let's say hyperbolic. So let's say this is hyperbolic. So we know that the regular ones are hyperbolic. We know that one can show that all the uniform ones are hyperbolic. But one can also show quite a few which are not. So one can show that the Fano, the Fano matroid is not, and also hyperbolic is closed until taking dual matroids, taking dual, so that it means that the Fano, but also the its dual is not also, I mean, the non-Fano, the Papus, there are quite a few that are not non-Papus and so on. So when you see a result like this, the Papus are not hyperbolic. So this is hyperbolicity does not characterize matroids, and so I guess there will be probably Nima might be talking about the right. So hyperbolicity is not the right characterization for matroids, and Nima in joint work with Cheyenne and others will show the right property for characterizing matroids. So I don't want to talk too much about this. Any questions?
So is
Is this the same as strongly Rayleigh matrix, or what is the difference? If you
yes, that's the same. Yes, yeah, that's the same, because that's going to be. I mean, so. I mean, I put coefficients of 1. You can also look at. You can put other coefficients.
Well, the thing is, as long as
But so if you have other, so if you look at polynomials with other coefficients, then you look at the support. So you want to look at the support of the so the monomials which are non-zero, and then so that's going to be the same as the strongly Rayleigh ones.
no, I'm saying as long as all coefficients are non-negative, they are the same, like
Yeah.
real stability and
Yeah. Exactly. Yeah. Right. That's what I. So stability and hyperbolic in all non-negative directions are the same.
No, I'm saying just one direction equivalent to everything.
Yeah, I mean, but yeah. So I mean, because once it's hyperbolic in one direction, the entire positive orient will be in the cone, and so it's going to be hyperbolic in all directions, in the positive orient.
Is it also true that if we pick E1, E2, and so on, EK from K plus, then Px plus sum of Si, Ei is stable?
I guess so, and
Yes,
he seems to say yes. So yes. Good. Let's take a little break. I actually don't have too much left. I should say that. So, for example, I mean, maybe before taking a break, and maybe we can finish only, is that among these. So I said if you have a that you what could happen is that so even though so from if I take, for example, so if I look at the cone corresponding to such a P, so there might be many P's that represent the same cone. So for example, if I take just a power of P of X, if I take a power of P of X, then that would represent, so the zeros will be the same, and so the cone will be and so one question is that if you take a hyperbolic polynomial, so I mentioned whether it has a spectrahedral representation, but so you could ask, I mean, not just if P corresponds to one of these determinant representations, so the determinant of sum of xi ai, but you could also look at, for example, a power of P of x. And so one of the results that Peter Brandon has shown is that there exist matroids, so the Varmus matroid for which the for no power of P, you can represent it. You have a spectrahedral representation. That doesn't mean, though, that you might have different. I mean, you can multiply by other polynomials and get a spectrahedral representation. So let's stop now. I'm getting a bit tired, and I'm sure that you are getting tired as well. So do I have more things, more open questions to ask you? I mean, let me just emphasize again that, I mean, one thing that I mean, the reason, so I'm not exactly, I'm still not sure why they invited me to give these lectures. And so that's the bottom line. But essentially, I think they invited me because I feel that these hyperbolic optimization is, I mean, that these hyperbolic polynomials and cones is a beautiful mathematical theory, and there is these class of convex optimization problems for which you get efficient solvability provided you can compute these polynomials essentially for free, and so that's extremely powerful. And so I mean, one thing I'd love to do is to be able to find, as Sasha Barvinok asked, so a nice application of it, maybe for discrete optimization or for some other class of problems. So that's my, certainly tomorrow in the talks in the morning, you'll hear more about these determinantal representations, so these questions about spectrahedra. And but one thing I would love for you to do is to find a killing, for example, discrete optimization problem for which hyperbolic programming optimization is the right tool to use. So maybe let's. That's my big open question, and I'll stop here. I mean, I think you should ask Cheyenne or Nima. So Nima, for example, when he gives the talks on Friday or tomorrow, I don't know exactly when he gives the talks, but that might be, no, he's not convinced.
No, you can define like some cone for log concave polynomials as well. So, okay.
Barrier, you don't have a natural.
Yeah, okay, yeah, that it's still new, so maybe you give it some time.
I mean, I guess one comment is that this log P barrier function, the self-concordance property that were mentioned, those are exactly the properties that are used in the last step of the Cadence-Singer proof from the morning that I couldn't get to.
Yeah.
So far, while this stuff, I mean, it's been used in proving mathematical theorems, but has not actually been used as an algorithm.
So just one comment again. One thing I've been trying, for example, to use elementary symmetric polynomial, the cone of it. And like one thing I find hard is that it's even not easy to describe the cone. Like, okay, it's like the vector is such that this is non-negative.
Yeah, I know.
I have no idea how to think about it. So I don't know if
ask Pablo and London and others. So again, I'm delegating to the audience. No answer, no good answer to that.
Okay, well, thanks.